Kia ora, Year 12. Here are two more questions from last week's test. The first one is one where we end up using integration by parts, and the second one is a complex numbers one. And one of the complex numbers bits in here is a question that comes up over and over, which is how we find the two square roots of this complex number. And we're going to work in rectangular form for this question. Okay, so let's take a look first at the integration problem. So this is 4 marks, so you can tell it's not going to be too much work. We have to find the integral of this. So the integral between 2 and 1 of x times the natural log of x dx. So let's just have a look and see why we're going to try integration by parts. Well, I've got the natural log of x here, and we know that we can differentiate that easily, but integrating it is a pain. And we've got x here. So we don't have anything like the derivative here of this thing here. And we've got a product. So it's going to be IBP. The next thing to do is to choose what to do with each bit. And it's really easy to differentiate this, but it's hard to integrate it. So this is the bit that I'm going to leave in the first round. And so the x is going to be the bit that I integrate. And then I'm going to differentiate the log of x and integrate this. Now notice that this is slightly different from the pattern we sometimes get, because when I integrate the x, it's going to get worse, right? It's going to go to x squared on 2. But it's really the only smart choice to make here, because we can't integrate this except by using IBP. Okay, so if we get on with it, we're going to integrate the x, so 1/2 x squared times the natural log of x, evaluated at the limits, minus the integral of between 2 and 1 of 1/2 x squared times 1 over x dx. So that gives me, I'm just going to leave this here for now, minus the integral of 1/2 x dx. So the whole thing comes out to be this. Now substituting in, don't hang up because I'm actually going to go over how to integrate log of x, and then we'll do the complex numbers stuff. So we've got what? Let's take the half. No, let's just do it like that. So I've got 1/2 times 4 times the natural log of 2 minus 1/4 of 4. Take away 1/2 of log of 1 minus 1/4. That gives me 2 log 2 minus 1. This is 0, and then I get plus 1/4. Feels like something's gone wrong there. Oh, you know, that's right, equals 2 log 2 minus 3/4. So there you go. Now, Eric was asking what we do about integrating the natural log of x, and we don't do that in this problem, right? Because we choose the log of x to be the bit we differentiate. But if I have to integrate the log of x, this is kind of a classic maths question, because we look at it and we just can't see what to do. But we can force it to be a product like that. We get 1 times the natural log of x. And then we're going to make this one be the bit that we either leave or differentiate. And we'll do 1 as the bit that we integrate. And if you do that, you'll get x ln of x minus x times 1 over x dx. Pretty sure we did this in class, but I'm not sure if all of you were there. X log of x minus the integral of 1, so it's going to be minus x plus c. And if you differentiate that back, you'll see that you end up back with the natural log of x. Okay, quickly getting on now to these complex numbers questions. There are quite a few of them, right? So this was quite a big part of the test. First, we've got to find the square roots here. Then we have to do some very easy manipulation of this, sketch this, and do something with the length. So these last 3 questions were quite straightforward. Right, let's look at how we do the square roots of a complex number. Well, we start off by saying, I'll just work over here, let the roots be x plus iy. So what we're looking for is a number that when we square it will give me -3 plus 4i. Expanding that, gives us x squared plus 2xyi minus y squared. And that equals negative 3 plus 4i. And you should by now be able to see what we're going to do. We're going to match up the real part and we're going to match up the imaginary part. So we get x squared minus y squared is equal to negative 3 and 2xy is equal to 4. I'm going to replace y with 4 over 2x. So I'm going to rearrange this. Y is equal to 2 over x. I'm going to take this and I'm going to substitute it into here. And this is the same pattern we're going to do whenever we have to find the square root of a complex number. This is done in textbook 11B, and I think it's question 10, and it's done in lots and lots of past papers. So we get to this, we're going to get a quartic. I'll go slowly. So x squared minus 4 over x squared equals negative 3. Multiplying everything through gives me x to the power of 4 minus 4 is equal to negative 3x squared. So x to the power of 4 plus 3x squared is going too fast, minus 4 is equal to 0. We've got a disguised quadratic. We'll use u squared plus 3u, take away 4 is equal to 0, and that factorizes really easily. That gives me u here, and we're going to do minus 1 and plus 4 to generate the plus 3u, giving me u is equal to negative 4, or u is equal to 1. Right, but u was simply x squared. So this has no real solutions. And this one has x is equal to 1, or x is equal to negative 1, and y is equal to 2 over x, which is 2. So here y is equal to 2 over negative 1, which is negative 2. So that gives me, I'm going to come back and talk about this in a second in case you're getting annoyed. The roots are z is equal to 1 plus 2i and negative 1 minus 2 root I. And you can check that if you square that, you will indeed end up with what we want, which is 1 take away 4 plus 4i, which is negative 3 plus 4i. And you'll get the same thing if you do that one, because it's just negative 1 times all of that one. Okay, the last thing to notice is that when we're doing this, we want the roots to be x plus iy. And I could have said here that what I'm after is a standard complex number where x and y are real numbers, right? Because if they weren't real numbers, we would just have another complex number that did have real numbers. Okay, so that's that one done. That was worth, I think, 4 marks, and that is a nice thing to be able to do. The other way, of course, that we could do it is we could use polar form on it. And I'm not going to do that here because I don't want to run out of time, but it's very easy to do square roots or any roots working with polar form. Okay, so we would just set up z is equal to r cis theta, and then we'd have this. R cis theta squared is equal to this in polar form. Okay, I won't keep going because I said I wouldn't keep going. Next one, complex number z is given by this, and we have to get it into our usual form. So that's coming up now. Then we have to sketch on an Argand diagram the numerator, the denominator, and that one divided by that one. Okay, so z is equal to negative 1 plus 3i over 2 plus I. We're going to multiply the top and bottom by the conjugate, and that gives me 4 minus negative 1, so 4 plus 1 here. Carefully multiplying everything out, we get negative 2 plus 6i minus I times negative 1 gives me plus I, and then minus the 3i squared gives me plus 3. That gives us 1 plus 7i over 5, and we'll split that up so that we've got the real bit 1/5 and the imaginary bit 7/5 I. Okay, that's that one done. Now, the next question looked hard. It wasn't hard. This thing here is C. So this is C. This top line is A, and this next line is B. I'll just go back to the question to show you what we're doing. So, show on a sketch of an Argand diagram with origin O the points A, B, and C. Okay, so A is here, B is here, and C is the whole thing. We're going to do that reasonably accurately, and then we're going to state an equation relating the lengths OA, OB, and OC. So that's probably the easiest mark in this whole paper, as long as you can see what they're getting at. So let's do a nice diagram roughly to scale. So I'm deliberately not just plonking this in from GeoGebra. Let's see. So A is -1 plus 3i. So grab your ruler and be accurate. So there's, it's not letting me be accurate. Well, okay, hopefully OneNote's going to come back. It's just done this weird glitchy thing. Right, where's it gone? Okay, we've lost our diagram. Okay, so -1 plus 3i is about here. You're going to do this with a ruler. B is 2 plus I. So 1, 2, 2 plus I is here. And then C is 1/5 plus 7/5 I. So C is here. And you're going to have some nice scales here with some numbers. So that's 2, this is 1, this is -1. That is a terrible diagram. Okay, if anyone's watching this, we're just going to start again. Okay, so I've just fixed that up because I couldn't stand it. So make sure that you do label all your points, and this bit here we should label as the real axis, and this bit we should label as the imaginary axis, and we should put some numbers on. And the last question is just asking, state a geometric relationship between the lengths. And I think you might have forgotten that when we're working in polar form, we know that if we've got R1 cis theta 1, R2 cis theta 2, that's just the same as this. So in this case here, we've got Z is equal to that. What we can say is that the length of that whole thing there is just going to be the length of the numerator over the length of the denominator. In other words, OC is equal to the length of OA over the length of OB. So if you spot that, very, very easy 1 mark. Remember that we've got multiply the moduli and add the arguments, and here we've got divide the moduli and subtract the arguments, which doesn't really work as a cute thing to remember. All right, thanks for watching. I will try and do some more of the test. If you've got any questions that you especially want done, just shoot me an email and I'll do those first.